in Richmond, the air quality progressively getting worse overnight.
This morning, Crozet was listed as having the worst air quality index in the state.
Be prepared for Charlottesville to have some unusually high air pollution levels.
On December 5th, President Jim Ryan hosted his traditional Run with Jim event. However, no one was able to attend due to concerns about air quality conditions. Unfortunately, due to complications caused by these circumstances, Jim collapsed mid-race and is currently receiving treatment in an extensive care unit. He will never run again. Share your past journeys with us using #IRanWithJim.
With climate change bringing unprecedented weather conditions, many parts of North America have experienced an increased threat from wildfires. As many of you have personally experienced this past summer, wildfires raging throughout Canada spread their smoke and unhealthy air conditions throughout the U.S., including into Virginia. As a result, many people had to shelter in their homes because the air outside would be harmful to breathe in. With an uncertain future ahead that could even affect Jim Ryan, machine learning models will help us mitigate the effects of these wildfires. With this idea in mind, we went to Kaggle to search for a dataset. We found a dataset that contained data on wildfires that occurred in the U.S. from 1992 to 2015. The dataset consisted of around 1.88 million rows and 39 features, where each row described data on a specific wildfire. We limited the data to include only fires that occurred in Virginia, and dropped features that were not relevant for training our models.
A crucial strategy in mitigating the impact of wildfires is early intervention. It gets exponentially more difficult to put out a wildfire as it gets bigger. The key to combating wildfire lies in having optimal locations for fire stations to quickly act on wildfires. This is where K-means clustering comes into play, utilizing vital features such as latitude, longitude, and fire size to pinpoint the most effective deployment sites. The versatility of our K-means model allows the fire stations to adjust the number of deployed stations by adjusting the K value. Furthermore, in cases where the fire department faces uncertainty regarding the optimal deployment of new fire stations, we can provide guidance on the appropriate number by assessing the inertia of various K values. Upon analyzing the current graph, it becomes apparent that the inertia experiences a sharp decline from a K value of 1 to 5 and then exhibits a more gradual reduction thereafter. This pattern indicates that the most efficient number of fire stations might be around 5 or 6, as the inertia tends to stabilize at that point. But our approach goes beyond general deployment. Recognizing that certain areas are more prone to larger wildfires, we've developed a K-means clustering model for differing sizes as well. By focusing on fire sizes between 10 to 50 acres and those exceeding 50 acres, we've honed in on locations that demand specialized fire stations equipped to handle bigger wildfires. This targeted strategy ensures that resources are allocated where they're most needed, enhancing the efficiency of wildfire response. For instance, if a fire station decides to establish 3 new fire stations to combat significant fires, they can strategically place them at the marked locations shown on the graph. The K-means clustering model also provides valuable insights into wildfire patterns. The graph illustrates that a significant number of wildfires occur in Southwest Virginia.
In addition to traditional wildfire fighting, which is largely reactive, it can be pretty beneficial to take a proactive approach and prevent them from happening in the first place. In order to aid this proactive approach, we decided to develop a classifier that will take in data from after the fire has been put out and predict the root cause of the wildfire. This will be largely beneficial to wildfire fighting agencies and their investigators, as a large percentage of wildfire data has missing data on the root cause, because it's pretty hard to obtain. In order to develop our classifier, we needed to create a new feature for the duration of each fire. In order to do this, we took the start day and time, as well as the end day and time of each data entry, and just subtracted them from each other. However, we were unable to use a lot of the data set because of this, because around 3/4 of the data set was missing data for the end day and time of the fires. We tried out many different models, including logistic regression, decision trees, k-nearest neighbor, neural networks, and random forest. In the end, random forest turned out to be the best performing model with around a 62% accuracy. Although we will be unable to determine the root cause of a wildfire with extreme accuracy, we will be able to provide the wildfire investigators with valuable insights into the most probable causes, helping out with their investigations and hopefully improving the actions taken to prevent such fires from happening in the future.